So guys, once we have done with respect to the pyrometallurgy, in our next session we are going to see that how we are going to extract the metal from electrometallurgy. So of course we know that in pyrometallurgy what we choose as an equation that our delta G should be negative, and as an equation we chose it as a Gibbs-Helmholtz equation, which was giving you as delta G is equals to delta H minus T to delta S. So utilizing this reaction, of course, by using or calculating the delta G value for your reduction of your metal oxide and oxidation of your reducing agent, we were getting the overall delta G of the reaction as negative. We were able to say that the reaction was spontaneous in the case of pyrometallurgy. But coming in the case of that of your electrometallurgy, of course, we are going to choose that of your delta G value itself. But we know that in electrometallurgy, neither we are going to supply the heat, nor the state is going to change in a very enormous way. So of course, the another delta G equation you have to know over here, which is given as delta G is equals to minus of N F into E naught. Yes, as you know, the delta G is nothing but of your standard Gibbs free energy, whereas N represents over here as number of electrons, F is that of your Faraday's constant we can see, and that of your E as the electrode potential of your redox couple, which will be formed in the system. So depending upon this equation, we are going to say that whether our extraction of the metal will be spontaneous or not. So of course, taking the electrometallurgy part, I'm going to write it once again, minus of NF into E naught of this cell. So in order to get my delta G naught as negative, of course, the N is a constant, which is your number of the electrons. Your Faraday's is a constant value, 96,500 coulombs actually, which will be seen in your later chapter of electrochemistry. But the only one thing which will be varying over here is that of your E naught of this cell. So that E naught of this cell, of course, this also involves two important reactions. One is that of your oxidation part and another is that of your reduction part. So whatever the redox couple you are going to get, we are going to see that electromotive force or the electrode potential, and in that case if I am getting the E naught as positive, of course what happens, the negative part of the reaction remains and I would be getting the overall delta G value as negative. So when such a case is happening, so what happens, the less reactive metal, that is when delta G will be getting you negative, in that case what happens means your less reactive metal will come out of the solution, and more reactive metal will go into the solution. Let us take an example. I am having a solution of Cu2+. In that I am having my iron as that of your electrodes. So when I am doing this process, in this case if delta G is negative, what happens? The less reactive metal will come out of the solution. That is what, of course, this is my solution part, Cu2+. So the less reactive metal is coming out of the solution. How it is coming? Of course, this was in aqueous medium, this is in the solid medium. Now this Cu2+ is getting extracted and coming out as that of your copper solid. And the more reactive metal, that is your iron over there, that will now go into the solution, that is from solid to the aqueous. So you will be getting as Fe2+. So now you can ask me, sir, how can we see which is your less reactive and more reactive? If you are remembering, I gave you an electrochemical series when teaching that of your redox reaction. By utilizing that electrochemical series, we will be able to say that which will be acting as a more reactive metal and which will be acting as that of your reactive metal. But in order to understand this reaction, first and the foremost thing, we have to understand this equation. That is delta G naught is equals to minus of NF into E naught. And in case if the two reactions, whatever the two reactions taken, that is oxidation and the reduction, in measuring that electrode potential part, if we are getting the positive, then only what happens, your less reactive metal will come out of the solution and your more reactive metal will go into the solution. So this is the main principle of that of your electrometallurgy. So in this electrometallurgy, we are having an extraction of your aluminium from that of your purified alumina. Purified alumina means it is nothing, it is just that of your bauxite. Bauxite main composition is your aluminium metal. So now we are going to see that how we are going to extract your aluminium from that of your aluminium oxide. Of course, it is an electrolytic process. So first and the foremost thing, let me make you certain things clear. Of course, in this process, we are going to use a cathode. So what do you mean by cathode? Of course, it's an electrode. What charge it will be having? Of course, it is a negatively charged electrode. Negatively charged electrode. So cathode, towards the cathode, what would be coming? Your cations, alva, which are positively charged species. Positively charged species. Similarly, coming that of your anode, what we know, it is a positively charged electrode. Yes, positively charged electrode. And that of your anions, they are negatively charged species. Very good. And the most important thing now we have to remember that what would be happening with respect to the electrons. That is, where does the electrons are gained and in which electrons the electrons are lost. I will give you the hint. Of course, the favorite team for the Karnataka is that of your RCB, Royal Challengers Bangalore, which can be said according to the chemistry as what? Reduction at cathode body. Reduction at cathode body. Of course, we know in terms of electrons that reduction means what? It is gaining of electrons. It is gaining of electrons. So what is happening at the cathode? The electrons are gained. Similarly, OA. If you want to call someone, we'll be calling it OA. The same way. What you can see over here at oxidation at anode. Alva. So oxidation means what over here? It is loss of electrons. That is, at anode the electrons are lost. So this is the main thing one has to know when we are dealing with this purification, or we can say extraction of alumina from the top of your purified alumina. Yeah, extraction of aluminium from your purified alumina. So of course, first and the foremost thing, let us see the setup, how the setup is. So this is actually your setup. That is, they have used, so guys remember, whatever the apparatus we have chosen over here is for the extraction of aluminium from your purified alumina. So whatever the vessel we are going to use over here is a steel vessel. Okay, that steel vessel has been coated with, from the inner part has been having a lining of carbon. So please remember, once again I am repeating. So whatever the outer part we are seeing over here is a steel vessel that has been lined from interior your carbon, or we can say as a coke itself, carbon lining. Do remember that this steel vessel which has been lined with that of your carbon, it acting as that of your cathode. Okay, that is your negatively charged electrode. Steel vessel which has been lined with that of your carbon is acting as a cathode. Same way, the part which you can see here as a bars, so these are actually your graphite rods. These are actually your graphite rods. So these graphite rods are acting as anode, that is your positively charged electrodes. You can just see here they have given you the positive sign indicating these are positively charged electrodes, whereas that of your steel vessel has been given with a negative sign, that is these wires are going to connect to their respective potentials. So remember that. Once again I am saying the steel vessel coated with that of your lining carbon is acting as that of your cathode. Whatever they have asked with a cathode, give a cathode for your pure extraction of aluminium from alumina means you should able to write it as steel vessel with carbon lining, and that of your graphite rods is acting as an anode. Do remember, whatever the solution you are going to take in this vessel, that will be mainly having a molten aluminium, that is your purified alumina, which will be in a semi-solid state. Do remember, this alumina is further added with a cryolite, that is Na3Al(F6). So this cryolite is acting as an electrolyte. Okay, very much important. In this extraction of aluminium, we are adding an cryolite which is having a composition, you could just see Na3Al(F6), which is acting as an electrolyte, and they are not mentioned over here. Along with this, we are also going to add a calcium fluoride, that is CaF2. So along with this cryolite, we are also going to add what? Calcium fluoride. Remember this CaF2, why we are adding means in order to lower the melting point, yes, of this molten alumina, and also to increase the conductivity. So in order to increase the conductivity and to lower the melting point of this alumina, we are adding what? Your calcium fluoride. Whereas that of this is also called as what? Fluorospar. Fluorospar. So cryolite is acting as an electrolyte, whereas fluorospar is acting as that of your lowering the melting point and to increase the conductivity. Now the question arises that what is happening over here? Let us now go on with it. Of course, what is happening? We know what we have taken our alumina part, aluminium. Of course, aluminium is a metal. So aluminium being a metal, what happens now? It is coming out from that of your purified alumina as Al3+, which is a cation. Of course, this cation, where it should go? To that of your cathode. So what happens over there? Al3+ is coming towards the cathode. But what happens at the cathode? In the cathode, gaining of electrons takes place. So Al was needed in the 3 electrons, and that would be given with respect to your cathode to give you that of your aluminium. Is that clear? Coming with respect to the anode is very much important. So at anode, of course, we have used that of your carbon rods, that is your graphite rods. So at anode, what is happening? So whatever your Al2O3 was there, that is getting split up when you're passing the electricity. That is as Al3++ 3O2-. Of course, alva. So Al3+ came towards your cathode. Now what happens to this oxygen? That will go to your anode. But what happens, since our anode is what? It is completely made of your graphite rods. So that graphite rods is mainly the main composition is carbon. So that is whatever the oxygen which is being coming towards the anode, that will react with the carbon to form what? Carbon monoxide. Similarly, once again, whatever the remaining part will be there, that will be also react with that of your carbon rods, that is your graphite rods, to get off your carbon dioxide. That is the reason, guys. Now you have to pay attention over here. So when we are carrying out this extraction of aluminium, again and again we are going to replace this anode. Why? Because the main composition of your anode was a graphite, that is the carbon content. So whatever the oxygen we are being produced over here, that is going to react with that of your anode. So what happens? The thickness of the rod goes on decreases. So at some time, complete utilization of the anode takes place. So at that particular moment, what we have to do, once again, we have to replace the anode with respect to that of your graphite rods. That is the reason what we are saying in this process is, that is the reason again and again for some interval of the time, we are going to replace these graphite rods. There is a reason. If, for example, 1 kg of aluminium, if we are going to extract, means nearly 0.5 kg of your graphite rods will be utilized. So you should only remember that how much in industrial process, at what interval of the time they have to again and again replace this anode. There may be a question, why in the extraction of alumina from purified alumina we are going to replace your anode routes? It is mainly because whatever the oxygen which has been produced in this process is going to react with that of your carbon, leading to its minimum thickness of your graphite rods. That is the reason again and again we are going to replace your carbon rods as that of your graphite rods. Okay, remember guys, this process, that is your extraction of aluminium from purified alumina, it is also called as that of your Hall's-Héroult process. Hall's-Héroult process. So they can ask you in any way. Give a part of your Hall-Héroult process. Hall-Héroult process. So give the extraction of aluminium from that of your Hall-Héroult process. So you should be able to say what you are going to do in it. Either names they can give you, or extraction of aluminium from purified alumina they can ask you directly, or they can also ask you give the extraction of aluminium from your Hall-Héroult process. The major important thing we have to remember over here is what is the main thing you are going to use. So in the Hall-Héroult process we are using the cathode as what? Yes please, steel vessel which has been lined with carbon, that is acting as what? As your cathode. Coming to that of your anode, what you are using? We are using that of your graphite rods. Yes. So coming with respect to the vessel, whatever you are taking, we are taking that of your molten aluminium oxide, plus we are adding cryolite Na3Al(F6). So this is why we are adding this one. It is acting as what? Electrolyte. Along with this one we are also been adding that of your fluorospar, that is your calcium fluoride. Why we are adding this one? In order to lower the melting point and increase the electrical conductivity. Yes. So at cathode what is happening? Al3+ which has been coming as a cation comes towards the cathode, gains 3 electrons and gives you Al. Whereas at anode what happens? Whatever the oxygen that has been liberated, that will react with that of your anode's carbon to give you carbon monoxide plus that of your carbon dioxide. So since these two are formed, what happens? Again and again we have to replace that of your anode. For every 1 kg of your aluminium extracted, 0.5 kg of your graphite rods will be used. Able to understand, I hope. So this is the main process of that of your Hall-Héroult process, which is coming under the category of your electrometallurgy. Electrometallurgy. Hope so it is clear with this. Okay, so in our next video we are going to see the extraction of your gold from your leaching process, or it's also called as that of your oxidation reduction method.